All right. So last week we talked about our families of functions, properties of functions, combinations of functions, transformations of functions. And so we basically finished our first week of pre-calc review, pre-calc summary. So we want to start to get into calculus-based concepts now. So maybe, I'm not sure if you guys do limits. I know in the last week of pre-calc, we usually touch on limits and maybe hint at some of the ideas behind limits, but it's not formalized and it's not really tested in the curriculum. So we really want to pick up with that in calculus. So maybe we'll see some piecewise functions as well. So we didn't fully go over piecewise functions last week. Make sure to take a look at some of that stuff in the book or any of the online resources I was just mentioning to you guys. So we want to talk about, well, what is a limit? So let's say, suppose we have a function. So suppose SPS and our function is going to be 3x minus 12 over the square root of x minus 2. And our question is, what is f of 4? So with our typical functional evaluation, we would want to try to plug in 4 for our x values. But what's going to happen here? We'll get 0 in the numerator and 0 in the denominator. So this is going to be a special type of evaluation when we get to limits. As a strict function evaluation, this does not exist. There is no value. There is no specific value of the function at 4. Primarily, when we were talking about domains and ranges last week, we cannot divide by 0. And so plugging in 4 will give us a 0 in the denominator. We cannot do that. This is undefined or does not exist. So the alternative question is, how does the function behave near 4? So typically, when we divide by 0, what that's going to cause is a vertical asymptote. So if you're remembering your pre-calc, dividing by 0, dividing by a constant by 0 gives you a vertical asymptote in rational functions. However, this case is a little bit different. Whenever we have a 0 over 0, what happens graphically is there ends up just being a hole in the graph. And why is that? So 0 over 0 is going to be a case of what we call indeterminate forms. And what does it mean indeterminate? It means we cannot determine. We need more information. And why is that? These forms are going to come up whenever we have sort of mathematically contradicting rules or mathematical rules that imply two different things. So for example, we know that we cannot divide by 0. Anything divided by 0 does not exist. It actually is going to give us a vertical asymptote. And in this class, maybe we'll explore a little bit of how that goes to infinity, or what types of infinities we want to be able to measure when we divide by 0. But conversely, if I have nothing, if I have 0 and don't have anything, well, 0 divided by anything should be 0. And so we have some contradictions here, because if I have 0 divided by anything, it should be 0. But if I divide by 0, it shouldn't exist. And so we have a little bit of a clashing rule system here. And what ends up happening is, well, as a value of the function, it doesn't exist. There ends up being a hole in the graph. But what we're going to see is that the behavior near 4 is rather consistent. So if we make a table, so I computed these beforehand. And for doing these types of tables, you will need a calculator. Because what we want to do is approximate some of the values near 4. So at 4, let's see, let's put 4 here. We can't compute any values, but I can plug in x values really close to 4. We can plug in 3.9, and if we do that, we'll find 11.925. So that's just 0.1 below 4. If we plug in something 0.01 above, so let's make this one 4.01, we get 12.008. Well, this is even closer, but slightly above. If we pick a number the same distance below, only 0.1 below 4, we're going to get 11.993. And we can check even closer and closer as we get to 4 what's going to happen. We will have 11.999. If we're slightly above by 0.001, we're going to get 12.001. So we can kind of see as we narrow in closer and closer, no matter which side, from below 4 or from above 4, we're getting closer and closer to 12. So ideally, we want that value to be 12. But because of this mathematical anomaly of dividing by 0, we actually don't have a value at 4. And so this is our idea behind limits. It's that sometimes the value of the function does not exist. There's a hole in the graph. We can't actually evaluate a function there, but we can get close enough. You know, as we get close enough from either side, we can get close enough to a specific value. So let's give the sort of arbitrary loose definition. We are going to end with the rigorous definition of limits in this lecture. So the concept of a limit is if f of x is defined near some specific x value, which we usually specify as x equals a, then we say that the limit as x gets closer to a of f of x is equal to L if we can make the values of f of x arbitrarily close to L by choosing x sufficiently close to a. So graphically, what is going on? Our function and so let's say these are 1 is growing, and I believe our function should look something, might not be right. It might be shifted up actually a little bit, I think. I think it might start slightly up. I'd have to check a graphing calculator, but our idea for any general function for a limit is that sometimes the function goes up and then there's maybe a hole there, but then it continues on. And so let's use some color today. And I'll explain this maybe a little bit better in an engineering context. The idea is, well, the value of this function, and forgive my graph, let's go ahead and adjust the scale a little bit, is right here is our 12. And the limit of the function there at that hole is 12, but it doesn't actually have a value. However close we want to specify, we kind of specify a margin of error around what the limit should exist. So we specify this margin of error around 12, and within that margin of error of our output, we can find a specific input. And for this function, it looks like our margin of error for the input is actually going to be fairly big. So as long as our margin of error for our input, for our x values, are within this red zone, the value of the function is going to be within the green zone. And I can shrink that green zone as much as I want. We can always find a specific red zone corresponding to our green zone, no matter how much we shrink our green zone. So our output is, think of it like the final product that we are producing in some sort of machine or mechanized production system. I want to shrink my margin of error. We have to meet certain standards for our margin of error. So based on the inputs of how we're designing this system, we need to know the margin of error for our other dimensions or for our other inputs. So some properties of our limits. And just some notes. For the full limit to exist, both sides must agree. So in our table, if one side was getting closer and closer to 12, but the other side was getting closer and closer to 15, then what we're actually going to have is a jump in the graph. There would be not just a hole, but one side would be coming up to 12. The other side would then jump up here to 15. The limit doesn't exist. Another way you can kind of think of a limit, if the limit exists, is I can fill in the hole if we needed to. We can actually just put a point there and it would make the graph fully continuous. So if there's a jump, we can't do that. The other thing to be careful of is the fact that we need any arbitrarily small x. Must produce a value close to the limit. So a function value. To the limit. So one example just to be careful of. In our last example, we chose like finer and finer points based on powers of 10. So we were 100th off, a 10th off, or a 10th off, then 100th, then 1,000th. And we saw that we got closer and closer. Let's take a look at a function, something like f of x equals sine of pi over x. You got to be careful with a context like this, because some functions get really crazy. So if we check something like, and we want the limit as x goes to 0 of f of x. So of course we can't plug in 0 because we'd be dividing by 0 inside the sine function. So if we check values getting closer and closer to 0, we can check f of 1 is just pi, that's going to be 0. F of 1/2, well, it's going to be sine of 2 pi. That's going to be 0. F of 1/3, sine of 3 pi, also 0. And you kind of see if we keep going, f of 1/10 is sine of 10 pi, gives us 0. F of 1,000th, sine of 1,000 pi, also gives us 0. So we need to be careful, because it looks like even though I'm choosing smaller and smaller x values, 1,000ths, I can choose 1,000,000th, but it's still going to be sine of 1,000,000 pi, and sine vanishes at integer multiples of pi. So it looks like our limit as x goes to 0 of sine of pi over x is equal to 0, but This is incorrect. Because there's values in between there. Even though we're choosing 1/1000th, 1/1,000,000th, there's always going to be values in between these integer multiples. So for example, we could check, let's just say add 1/2 to the denom, to the denominator. So say if we choose x is equal to, and I'm just going to write it as 1/1000 plus 1/2. So 1000.5. What's going to happen in this case? We're going to have f of, so pi over x, we'll take the reciprocal of this when we evaluate it. It will be 1000.5, or 1000 plus 1/2 times pi, which will be sine of 1000 pi plus pi over 2. And so what's that going to be? So 1000 pi, you got to remember your trig a little bit, or you could use an angle sum formula if you want. 1000 pi is going to be a multiple of 2 pi. So we're going fully around the circle 500 times. And then we're going how much further? Pi over 2. So this is actually going to give us a value of 1. And so what's the problem with this in terms of calculating the limit? That, well, we have a lot of values at 0, and as we get closer and closer to this value of 0, we should be able to choose, or as our x values get closer and closer to this value of 0, if the limit of the function, so if our y value was 0, then that means we should be able to we should always be very, very close to 0, no matter which x values we choose. However, we found some small x values that produce a value that's not very close to 0. So let's talk about one-sided limits. So when I said both sides must agree, that is for the full limit. We also like to be able to study and categorize one-sided limits as well. So primary example is going to be the use of this Heaviside function, which is going to come up a bit in this course. And this is a good example of a piecewise function. So we're going to use our typical bodies of functions that we developed last week, but now we're specifying domains for specific pieces of it. So if we were to try to graph this function, the function just says it's going to be 0 for all x values, or for all x or for all t values less than 0, which means the function is just going to be 0 up until 0. We'll have a hole in the bottom part, and then we'll be at 0. Our function value is 1, and then for any t value bigger than that, we'll still be at 1. So this is our Heaviside function, and we can now define our one-sided limits. So one-sided limits are defined similarly. So we say that the limit as x approaches a. Now we use a superscript with a plus or minus. So if we say minus f of x equals L, then our function value gets close to L as x gets close to A from below. So this minus, you think of just slightly less than A. So we're approaching from behind, from lower than A. In this case, our A value is going to be 0. And so as X approaches 0 from below, it just means we're picking X values below 0. So negative values. And then as those negative values increase to 0, that piece of the function approaches 0. Likewise for our right-sided limit. So from values above, we use a plus there. So I'm just going to use ditto signs as X gets close to A. From above. So in our example specifically, with the Heaviside function, actually, you know what? Let's do a new example. Let's make it a little more complicated. I want to do a full example. Yeah, and I think we've got time. Let's do a good example here. Let's draw a graph. So let's see. Let me draw. Some reasonable tick marks there. Let's make our function in red. So we'll put a hole there. We'll put a value here. Let's put maybe a graph like that. Let's put horizontal line there. And how else do we want this to look? Maybe a piece like that. So let's say this is some function f of x. A lot of things going on in this graph, a lot of different types of pieces. Now we could define f if we wanted to as a piecewise function. I'll leave that to you guys to practice some of those pre-calc skills to define functions that look similar to these types, whether it's a curve, maybe a parabola for there, maybe a circle on this piece. And let's compute a few things. So let's say the limit as x approaches 0 of f of x. Let's call this part A. Let's do B. Let's say f of 0. Let's do C. Let's say the limit as x approaches 2 of f of x. Let's do the limit as x approaches 2 from below. The limit as x approaches 2 from above. And let's do f of 2. So this kind of ties in everything together. We've got function evaluations, the actual point of the function. We've got limits, and then we've also got one-sided limits going on. So the limit as x approaches 0. So here at 0, or x value is 0, we want to look at the value of the function as the graph is approaching. So we're doing a limit, meaning if I'm approaching from the left, as x gets close to 0, the values of the function are approaching 1. And that 1 is from both sides. Can you guys see that green? Not really showing up. Let me use a darker color here. Let's use blue. So both sides of the graph are coming. We could fill in that hole at 1, and that looks like what the graph should be at x equals 1. And actually, I did this wrong, didn't I? Not even a function. I needed to put a hole here. This piece of the graph should not exist. Ignore this piece. But there is a dot right here. So f of 0, this means the value of the function. Where is the dot? Anytime you are evaluating a function, find the dot. So f of 0, though, is 2. That's where the dot is. So our limit is different from the value of the function. Let's move over to our x value of 2. Now, x value of 2, limit as x approaches 2. Well, what's going on with this guy? Let's actually leave that off for just 1 second because we can actually see the right and left-sided limits. Let's do these first. Our limit as x goes to 2 from the left, meaning we are picking x values slightly below 2, and then we are going to trace the curve. We are looking at the function values and where they approach. So x values less than 2, tracing the curve up to the x values of 2 means we're running right into this dot. So our left-sided limit is 0. The right-sided limit, so now if we pick values slightly bigger than 2 and then shrink our x values to 2, so our x values are decreasing towards 2, slightly bigger, and then the value we're approaching of the function, though, is up there at 3. So since the left-sided limit and the right-sided limit are different, meaning that if I trace the curve from the left and if I trace the curve above from the right and both shrink towards the x value of 2, we're touching different points. So this limit, the full limit, does not exist. However, the value of the function does. So the value of the function at 2 is where the dot is. And that's a 2. So all of those values can be different. The left-sided limit, the right-sided limit can be different from the function evaluation. The actual limit, if it does exist, can be different from the function evaluation. Sometimes they are the same. Okay, so let's work up to our rigorous definition of what is a limit. And we will explain this in a more engineering way. In a rigorous math way, it can get kind of complicated, and this is sort of an introduction to what would be called analysis in mathematics. So the limit as x approaches a of f of x equals L. So we say the limit as x approaches a of f of x equals L if for any epsilon, so this is kind of Greek letter epsilon stands for a small number greater than 0, there exists a delta greater than 0 such that if the distance that x is from a is less than delta, then the distance that the function is away from L is less than epsilon. What does this mean? This means that what do we want to specify first? So this is going to be, I think I used green previously. This is our final output tolerance. again, can you guys see that? I think I still need to use a darker color. Let me use a darker green. We want to specify the output tolerance first. So I pick, we know where the output value is. It's at L. But the value of the function doesn't exist there. So what we have to do is say, specify how close I want to get to this limit. Since I can't actually make x equal to a, since there's a hole in the graph, I can at least specify how close we need x to get to a. And how close do we want to be? Well, we need to know our output limit. We need to know how close our function is going to be to L first. And as soon as I specify that, we can find the tolerance for our input. So our input tolerance is going to depend on our final product. So this value here and this value here are going to be a minus delta and a plus delta. These upper and lower limits are L plus epsilon and L minus epsilon. So we have this epsilon range, or I guess our 2 epsilon range and our 2 delta range. So my tolerance, specify the tolerance for the output product, and then we can find the tolerances for our inputs. So real quick, sorry if anyone's writing still, let's do one example. Let's say we're building hex nuts. And the side length of the hex nuts is S, and the area based off of that is going to be 3 root 3 over 2 S squared. Suppose that our area needs to be, let's pick a nice number, something like 24 root 3 with a tolerance of, say, 0.1. And our tolerance is going to be this plus or minus 0.1. We want to find the tolerance of S. So our machining products, we need to know what's the margin of error we can have in their side lengths to make sure we have our margin of error in our final product correct. So our L in this case is going to be 24 root 3. That's going to be the limit of the function. However, our margin of error, our epsilon, is 0.1. Our A value is going to correspond to the specific S value. So if we have 24 root 3 equals 3 root 3 over 2S squared, we need to figure out the input for S. So root 3's are going to cancel. We'll divide by 3. When I square it, we'll get 16 is equal to S squared. So our S is going to be 4. So the specific value of the side lengths, we're going to machine our side lengths to be 4 meters, inches, however big these nuts are going to be. But then now what we want to do is find our delta. So we need to know the margin of error that we can specify our side lengths in order to meet the margin of error for our output. So how do we do that? We can essentially plug in the margin of error into our area formula and then solve for that similarly. The other things we can find are upper and lower bounds. Let's see, we're about out of time. So the rest, some of the calculations for this, you might need a calculator for, especially once we get into using decimals. But if we have something like 24 root 3 at the upper end of our margin of error, what we can do now is solve for our S. So our S, this will give us our upper bound for the margin of error of S. Likewise, if we do our subtraction, this is our lower bound for the margin of error in our output, or the lower bound of what we want our product to be produced at. We can find the lower bound in terms of our margin of error of S. So solve for S in both of those cases. The width of that, or the distance that is away from 4, should give us the margin of error. And I believe the other thing we can do is simply specify that I think if we just solve for 0.1 is equal to 3 root 3 over 2s squared, and then solve for our s squared, that might work as well. No, I think that'll be wrong. I think what we want to do is actually look for our delta this way. The problem is this factor here. I don't think that's going to work. In any case, you kind of want a calculator to go ahead and compute that, to finally and figure out and solve what your error bounds are going to be for your S in order to solve for your delta.